Hello and welcome to episode 14 of Random Topics with Jack, where we explore the intriguing and sometimes controversial topics that shape our understanding of the world. Last time we dove headfirst into the world of anime and it was an amazing journey. This time we're venturing into the wonderfully weird world of quantum physics. Don't worry, we'll keep it simple. We'll explore some mind-bending concepts like wave-particle duality, which is weirder than it sounds, Schrödinger's cat, don't worry, no actual cats were harmed, and quantum entanglement, like magic but sciencey, without getting bogged down in complex equations. We'll also look at how quantum physics is secretly making your life awesome, from the lasers on a Blu-ray player to the MRI machine that helps doctors see inside your body. Get ready for some seriously mind-blowing stuff. Now let's get started. Now some people might be thinking, quantum what now? Don't worry, I'll explain. For centuries, we understood the universe through classical physics. Think Newton's laws of motion, things like gravity and how balls bounce. Classical physics works great for everyday objects, but it kind of falls apart when you get down to the tiniest of scales, the worlds of atoms and subatomic particles. And that's where quantum physics comes in. It's the physics of the super small, and it's a bit weird. It's a whole different set of rules. One of the key ideas in quantum physics is quantization. Imagine a staircase. You can only stand on specific steps, right? You can't hover in between the steps. Well, in quantum physics, energy, momentum, and other properties are like those steps. They exist in discrete units called quanta, and it's not a smooth ramp. It's a staircase of possibilities. So instead of a smooth flow of energy, we have these little packets of energy, quanta, that are like tiny little Lego bricks, building up everything in the universe. This is totally different from the continuous smooth world described by classical physics. It's like comparing a smooth flowing river to a stream of discrete water droplets. This quantization is key to understanding how atoms behave, how light interacts with matter, and so much more. It's a fundamental shift in our understanding of reality. We'll explore some of the mind-bending consequences of this quantization in a minute, but for now, let's just appreciate the fact that the universe is a bit more like a Lego castle than we once thought. Now, first we're going to look at wave-particle duality. So imagine something that's both a wave and a particle at the same time. It sounds crazy, right? But that's wave-particle duality. Electrons, for example, sometimes act like little tiny particles and sometimes like waves. It's like they have a split personality. Think of it like this. Sometimes an electron behaves like a tiny marble, and other times it acts like a ripple in a pond. This duality is shown beautifully in the double-slit experiment. If you shoot electrons at a screen with two slits, they create an interference pattern, a pattern that only waves can create. But if you try to observe each slit where each electron goes through, the interference pattern disappears, and the electrons act like particles. It's as if the act of observing changes their behaviour. It's truly bizarre, but it's a fundamental aspect of quantum mechanics. Then there's the uncertainty principle, and this principle states that we can't know both the position and momentum of a particle with perfect accuracy. The more precisely we know one, the less precisely we know the other. It's not a limitation of our technology, it's a fundamental property of the universe. Think of it like trying to pinpoint a bee in flight. The more precisely you know where it is at one moment, the less you know about its speed and direction. This uncertainty is inherent in the quantum world. It means we can only talk about probabilities and not certainties. The universe at the quantum level is inherently probabilistic. And then we've got quantum superposition. And this is where things get really weird. A quantum system can exist in multiple states simultaneously until it is measured. It's like a coin spinning in the air. It's neither heads nor tails until it lands. The famous Schrödinger's cat thought experiment illustrates this. So imagine a cat in a box with a radioactive atom. If the atom decays, a hammer breaks a vial of poison, killing the cat. Until we open the box and observe the cat, Quantum mechanics says it's both alive and dead at the same time. This sounds crazy, but it's a consequence of superposition. The cat is in a superposition of states until we measure it. And then we've got quantum entanglement. And this is arguably the strangest concept in quantum physics. Two or more particles can be linked together in such a way that they share the same fate, no matter how far apart they are. If you measure the property of one entangled particle, you instantly know the property of the other, even if they're light years away. It's like they're communicating faster than light. However, this doesn't allow faster than light communication because you can't control the outcome of the measurement. It's a fundamental connection between particles, a spooky action at a distance, as Einstein called it. Entanglement is a key resource for quantum computing and other advanced technologies. So let's explore the strange side of quantum physics and its real-world applications. Quantum tunneling is one thing. If you ever wonder how particles can pass through barriers they shouldn't be able to, that's quantum tunneling. It's like they're ghosts that can pass through walls. It's not like they magically gain energy to overcome the barrier. They kind of borrow energy to get through it and then pay it back. It sounds impossible, but it's real. It's responsible for many important processes like nuclear fusion in the sun. Without quantum tunneling, the sun wouldn't shine. And then there's quantum teleportation, and no, not the Star Trek kind. Quantum teleportation involves transferring the quantum state of one particle to another without physically moving the particle itself. It's like copying the information of a particle onto another, leaving the original particle unchanged. It's not instantaneous movement, it's more like creating a perfect copy at a different location. It's a mind-bending concept with potential applications in quantum computing and communication. In talking of quantum computing, quantum computers themselves harness the power of superposition and entanglement to solve problems that are just impossible for classical computers. Imagine a computer that can explore all possibilities simultaneously, not just one at a time. Now, this could revolutionize fields like medicine, material science, and AI. Quantum computers are still in their early days of development, but they hold immense potential for the future. And here are some applications every day of quantum physics. One of them is lasers. They're a direct result of quantum physics, quantum mechanics even. They rely on the stimulated emission of photons, a quantum phenomenon that allows for the creation of highly focused beams of light. Lasers are used everywhere from barcode scanners to laser surgery. They're a testament to the power of quantum physics in our daily lives. Medical imaging techniques like MRI, magnetic resonance imaging, and PET scans, positron emission tomography, rely on quantum mechanics. MRI uses the quantum properties of atomic nuclei to create detailed images of the inside of the body. PET scans use the annihilation of positrons or antimatter with electrons, the quantum process that produces gamma rays that can be detected. These techniques are crucial for diagnosis and treatment of various diseases. Semiconductors, the foundation of modern electronics, relies on the quantum mechanical properties of materials. The behavior of electrons in semiconductors determines how they conduct electricity, making them essential components in computers, smartphones, and other electronic devices. Without quantum mechanics, our electronic world would not exist. And there you have it. We've just scratched the surface of the mind-bending world of quantum physics. It's a world where particles can be both waves and particles, where we can't know everything with certainty, and where what Einstein called a spooky action at a distance is a real thing. So we've explored concepts like wave-particle duality, the uncertainty principle, superposition and entanglement. We've seen how quantum physics is responsible for lasers, medical imaging, and the very foundation of our modern electronic world. And we've glimpsed the potential of quantum computing to revolutionize the future. Quantum physics is a fascinating and ever-evolving field, and we've only just done a very short episode on it. We might do a more in-depth episode later. but it is a reminder that the universe is a far more strange and wonderful place than we might have ever imagined. And if you are interested in learning more, there are plenty of resources available. Check out books like Quantum Mechanics for Mathematicians by James V. Voss and Eugene J. Saletan, or Quantum, A Guide for the Perplexed by Jim Al-Khalili. Websites like the American Physical Society and the Institution of Physics offer great articles and resources, and for a visual exploration, watch documentaries like The Fabric of the Cosmos by Brian Greene or The Quantum Universe by David Attenborough. So, like I said, just a short episode because I didn't want to get too deep into complex equations or anything like that, but we might pick this up and do a more in-depth analysis later. But next time we will be exploring the fascinating interplay between history and warfare. We'll be strategizing how historical conflicts have shaped modern military tactics and technology. From ancient battles to modern warfare, we'll see how the past continues to influence the present. And as always, I've been your host, Jack, and until next time, keep questioning and exploring.